Good afternoon and hello everybody. Welcome to Water Today's Master Program on remote monitoring of water and wastewater treatment plants using IoT, AI and SCADA. I hope all are safe and doing well. Today's training topic is very crucial for many wastewater treatment facilities, end user companies, plant operators and others responsible for smoothly operating their or their clients' treatment plants. During these times of the pandemic, with reduced manpower at treatment facilities or non availability of manpower to be physically present at the plant, it becomes imperative to remotely monitor the wastewater treatment plants. Some questions that arise then are: how can you make sure that your pumps are operational when water levels rise or when water quality exceeds the permitted pH quality levels? What are the current chlorine levels? What is the current pressure levels in my pumps, etc.? And the answer to these are monitoring the plants through Internet of Things or artificial intelligence connected to your water treatment system. You can see the exact status of your system at any time. This can help reduce on site visits by only making necessary service visits. Not only can you monitor your water treatment systems, you can even remote program or configure the integrated PLC system using the remote access mode. So, considering all this and more, our guest trainer for today, Mr. Prakash Muthuswamy, will take the session and give us a clear insight into the best practices for remote monitoring for your water and wastewater treatment facilities. Mr. Prakash has over 3 decades of India and international experience in instrumentation, automation systems, project and construction management, including supervision of consultants and contractors in terms of safety, technical, and financial aspects. His experience in water and wastewater, petrochemical, oil and gas, and power sectors, particularly on the state of the art RO desalination plants for potable water and MBR plants for wastewater treatment. He is a specialist in developing strategies for sustainable energy, efficient asset management in the water industry. Mr. Muthuswamy is experienced in master planning and development of systems such as smart utilities, SCADA, and CMMS to meet the business process needs. Testing and commissioning management for process plants, pump stations, and buildings infrastructure and identification of potential improvement areas. His experience in preparing performance-based contracts, managing used using sorry man, performance-based contracts managed using key performance indicators for asset management. He has also experience in infrastructure construction contracts management. As managing partner of automation and maintenance management systems, projects are ongoing, including high accuracy bulk water metering for the city of Mumbai, complete water network monitoring, and online NRV assessment for Thrissur in Kerala. I would like to welcome Mr. Prakash Muthuswamy and thank him on behalf of Water Today for conducting this program. I now hand over the session to Mr. Muthuswamy.
Very good afternoon, ladies and gentlemen. Good afternoon, Ramya. Thank you for the introduction and for the opportunity actually to discuss what is a very important subject in our country. Water has been, most unexpectedly for someone who has lived outside India for considerable amount of time. I came back and found out that water has indeed become a precious commodity in our country. Even in places where water scarcity was unheard of, we are having water shortages in the summer months and things like that. Now, add that to the scenario that our water infrastructure is becoming older. In most of the cities, we have 50. We've even seen some cases where water networks are over a century old. So with this aging infrastructure, without any concept of monitoring and managing water systems, our water networks have been operating, and we're all aware that the non-revenue water is to the tune of 40–50%. We're lucky if it is less anywhere. So this is the scenario in which our water industry is standing now. Couple that with the uncontrolled wastewater discharges and deficiencies in treating that, our water scenario is rather grim, and a lot of good work needs to be done to improve that. And one thing that, at the outset, what I would like to say is, if we continue to practice whatever we have been doing over the decades, then the results also will more or less continue to be where they were. So clearly, if we want to improve, we want to automate, and we want to be informed on the consumption pattern, we want to reduce non-revenue water and make water available for every being. That's the right of every creature, not just men. So in that scenario, evidently that we have to manage water a lot better. And managing water begins with good metering practices. Here again, that's a uh, very important area for careful consideration, because over the last 70 years, perhaps, we have not done much metering in water at all. We are way behind the in many parts of the world in terms of water metering. And even within that, when it comes to the technology we deploy in our country, we are not really conscious of what are the current possibilities in terms of measurement. We would go by what the textbooks have said 40 years, 50 years back in terms of water monitoring, and whereas in internet and in terms of other amenities, we are well in, and we are managing technology and utilizing it day to day, minute to minute in our lives. But when it comes to the very, very important aspect of water management, we completely forget to leverage technology. So, with this background, we will look at the course today. Broadly, we are going to look at clean water today and wastewater in tomorrow's afternoon session. Now, any information that you get is only as good as the sensor technology that you deploy. So, measuring and then sending the data somewhere, for monitoring it, having a display system for the data, and then analyzing it. These are all sequential processes which give you a lot of useful information and management capability. But what is most important is, what sensors do we use to measure the water, and how reliable are they? Now, for instance, there have been projects where in our country where you got to cut a pipe and install a meter. But because the water supply is continuous and it is critical, and there is a hospital that is supposed to receive water 24/7, you are not able to cut the pipe and install the meter. So the metering never gets done. Many are instances like these. So every location has got a very unique need in terms of metering. For example, you may have a gravity flow. It could be a low velocity flow or a partially filled pipe condition. You could have water carrying a lot of sedimentation. You could have clean water, treated wastewater. The water itself comes in different forms. Water with embedded flow, partial pipe flow, these kinds of situations. So you got to have the technology that works for you and that can deliver results in a timely manner. So a lot of our attention today will be in terms of the metering technology related to water per se. And then after measuring, how do you acquire that data? How do you control from remote? Then how do you have some analytics coming off it? After measuring water everywhere for a municipal corporation or for a city, how do you determine how much non-revenue water is happening? How much is the losses? Then some considerations of installation and maintenance aspects with budget, because in our country very important. I was speaking with a bureaucrat one time, and he was saying
Sorry
that,
to interrupt, Mr. Prakash. Your voice and video both are cracking. There is disturbance. The continuity is breaking.
okay, my internet seems to be all right. Uh, shall we switch to the other net? I have two options in internet, so I'll try to switch to another.
The video is pausing, so what happens is even the slides may not change. So, your video is paused right now.
Audible now? Ramya, can you confirm? Am I audible? Hello?
Yes.
Okay, that's good. So coming back, apologies for that. This internet, sometimes it does let you down. Uh, we were talking
So,
about
you
metering.
are on slide number 3 right now.
Yeah, that's
All
okay.
right. All right.
I'm seeing that. That's fine.
Okay.
Thank you. So we will talk about metering technology as a critical subject, and then how to gather the metered data and how to do analytics to arrive at an assessment of non-revenue water, how much you are losing, what are the maintenance and installation best practices. Because you buy the best instrument in the world, and if the installation is not right, it will not give the lasting good performance that you are looking for. And I just said before, we got interrupted, that I was speaking with an IAS officer in Delhi one time, and he was saying that in our country, if we get something wrong, then it might take 12 to 15 years to find a budget to rectify that, because there's a great deal of requirement. It's a big country, so to be able to rectify something or to redeploy, the cycle time could be as high as 12 years to 15. So that really means that when we install our metering, we have to get it right. There's no scope for trying something and then not succeeding. So we'll see some examples related to that. And then in terms of water treatment plants, what kind of automation strategies can we have? How can we make our operations more sustainable, energy efficient? That's the syllabus that's been circulated to you. With that, we will go into the subject. In terms of overall water network monitoring and management. So first we will look at water networks and then come to treatment facilities towards the end of the session. Here you see at the bottommost layer, what you must have is the physical devices, the sensor technology, the controllers, that as Ramya said in the introduction, PLC, programmable logic controllers that help you to do the automation, or the sensor technologies that measure the critical parameters, whether it is volume flows, pressure, level in systems, or quality parameters like pH or turbidity and some such. So we begin with the sensor level, and then there is the communication level, which is actually very, very well advanced in modern times. There are many telecom service providers, communication options are many, technologies are available. And more importantly, to carry the data, city-wide data to a central location, that process has become light. You have the communication protocols that can run economically, carrying data, nearly real-time data into your central system where you can efficiently operate and manage. So communication systems and connectivity give us a big advantage when it comes to water management or infrastructure management, world over, and also in our country. Then you come to the computing systems, where basically there is a signal conditioning and you receive the data in and say that I'm having so many MLDs of water flow, or how many bars of pressure have you in the system. Get that data read into a computer environment, and accumulation of the data day after hour, day after day, yearly, storage of data and subsequent analysis. Extract the data, analyze it, even take it above the application environment into the management decision taking environment. First of all, operationally you need to be, that's at level 6. You have operational requirement, where what is happening, what are the flows in my network, am I having some burst pipe that my water flows has increased in the network. So that's operational data. And further above that, for infrastructure planning, nowadays we are having a lot of these umbrellas or smart city projects, and the smartness should actually come from how we deploy the technology, isn't it? So if we are improving the infrastructure of a city, then the metering is going to come at the tail end after 3 or 4 years of infrastructure improvement. And how would you find out what improvement has actually taken place in the system? Because earlier, remember, when we started, there is no quantification, there is no proper record of how much water is happening. So there is a need for the low-hanging fruit, to get early data and then watch your network as improvements happen, and ensure that not only you are improving, but you are maintaining that performance level that is expected. So these are all the different layers that modern systems in terms of real-time water network monitoring. Let's move on. Let us begin specifically looking at the metering technologies. Now, what I would like to say here is, I think the intention is that if there are and we need to interact, then we can reserve that right till the end, and then we can have an interactive session. So I would request you to keep a tab on what questions you have, so that at the end of the session we can come back and review that. Now, in any water system, whether the water is moving in an open channel, a river, or in a pump system with storage reservoirs, etc., level measurement is a key parameter. Now, there are various ways of measuring water level. The most commonly used one in terms of our municipal water systems and even open channel systems is a non-contact system. That is an ultrasonic level measurement system. Ultrasonic means, obviously, as the name implies, the usage frequency is higher than the audible sound that we are having. So it is in the kilohertz to megahertz range, is what we call ultrasonic radar, and these type of what happens is a generated that comes down from the sensor and hits the surface of the water body and reflects back. So the time taken for the sound to travel from the sensor downwards and then back again upwards into the sensor, that time is proportional to the water level, and that is the measurement principle in an ultrasonic level measurement system. Now, where do you have to measure level? Normally in pumping systems, intake of a water treatment plant, or below ground or overhead storage reservoirs. It's very important to monitor the actual water level for two reasons. One is you need to make sure that you are utilizing the available storage space. Well, what happens if there is an emergency in your pipeline has broken and you don't get any supply for a few days? You will be depending on water stored in the tank to keep supplying water to the users, So it is important that you maintain sufficiently high levels of water in the storage tank at all times. And this also is important in terms of safety, many cases where you need water for firefighting and some such issues. It's important that you maintain the water level in your tank. But on the other hand, you could also be having overflows in trying to maintain full tanks. You may be losing water continuously through overflows, etc. So you want to level and maintain water at a level that is optimal. And this is how an ultrasonic level transmitter is working, as I said. Other important consideration is normally these devices are made ingress protected IP68. Now, ingress protection is a very commonly used word in measurement. Now, when I say IP68, IP stands for ingress protection. And then the 68 here, the first digit stands protection from solids ingress. And the second digit stands for protection from liquid or water ingress to the instrument, to the electronics. So here, the first digit IP6 means that it is dust tight. No dust, no atmosphere, nothing outside will go into the sensor. And the second digit 8 means that it is watertight, sealed. So even if it is submerged in water, the instrument will not be damaged. Now, when you are putting, etc., it is very important to have this IP68 sensor because the water may sometimes come up above the sensor level, and if water goes into the electronics, it will destroy the sensor. So that's the IP rating. Sometimes you have panels which are IP65. If you say 65, then you can understand that it is meant for outdoor use. It will go in, and also if rainwater was to fall on it, it will not increase and damage the instrument. If you say IP66, then that means that even if you hold a hose, wash the electronics, the transmitter with a hose, no water will go into it. Then 67 means it can withstand effects of ingress of water. Even it is submerged, short distance submergence, it can withstand for specified durations of time. And 68, of course, is completely watertight. And also, you find the panels in terms of dust ingress, etc. You have IP55 panel. 55 means you allow some fine particles, dust and all can make way. So that such a panel will have like an air filter of some description installed. So it will try to keep the dust away, but there could be an element of fine dust that goes into the panel. So like this, this is itself a subject, so we will not go into all the details, but suffice it for us to say that IP rating is an important aspect for looking at instrumentation. And you need to be able to set up, when we say some of the features here, how to set up a parameter when you are setting up an ultrasonic level sensor. You need to say, okay, am I in a tank that is 5 meters deep, or am I measuring in a tank that is 10 meters deep? What is the depth of measurement that I have? Like these parameters have to be set up. Now you see in the screen in front of you, and with a keypad, and that keypad allows you to go and set your parameters. What signal do you want from this device? How do you want to utilize the information that comes from the device? All of these can be programmed from a menu. It is all menu driven. Typically, you will go in parameter 1, 2, 3, 4, 5, 6. You set all your required parameters, and the instrument is up and running. So, from installation to operation, it's a matter of minutes, an hour maybe, to get an instrument up and running. That's how the modern measurement systems are there. Now, of course, it is when it comes to level measurement with ultrasound, it is important to make sure that you have temperature compensation, because the velocity of sound in air varies with temperature. So when you are using an aspect of the sound, then variance in ambient temperature should not affect your measurement accuracy. So we talk about temperature compensation. That is applicable in many cases. For instance, if you are measuring pH in a water treatment plant, what is the pH of the water that's going out? And there also temperature has got an impact on the pH, so the measurement needs to be temperature compensated. These are all, although here we are looking at level sensor, but some of these aspects are applicable for measurement in various heads, in analytics, in other flow measurement also there is temperature compensation, where the variance of temperature can have an impact on your measurement. That is when you compensate for it. Now, finally, what we said, very short startup and measurement times and very low energy consumption. So if you are in a location where you don't have a power supply, you can run a level sensor on battery for considerable length of time quite efficiently without bothering to bringing power supply to the location, etc. So this is one way of level measurement, that is ultrasonic level measurement. And of course, there are other ways which could be looking at the pressure, hydrostatic head. So seeing two sets of pictures. Above, you are seeing some like a plant process installation, and down below you are having a closer look at some of the sensors that are involved. Now these are all measuring hydrostatic head of water above the sensor. So if you're having 2 meters of water above the sensor, then the instrument will measure those 2-meter head as a function of the pressure. And what you have is you have a sensor which is made of ceramic or a capacitance type sensor or some such. The sensor is hanging from its own cable into the process area where you are measuring. Now, comparative measurement, that's one thing that I would like to point out to you. What you are seeing there is relevant to water systems where you are having screens. Screens are devices, mechanical devices that stop suspended solids from going into a treatment plant. So what happens when the screen gets blocked? The level upstream of the screen will start to go up, and the channel after the screen will get emptied. So you get differential level there. That is why it is called comparative measurement here, because it is looking at the level before the screen and the level after it. Ideally, in a free-flowing condition, both would maintain the same level. But as more solids come and they block the screen, the level will go up in the upstream side and it will go down in the downstream side. So based on that differential level, you can decide whether your screen is working well or it is blocked. And the same can be used for wet well, like wastewater or a clean water storage tank. You can also convert it and measure in volume. So if I have 5 meters of water in a storage tank, how much volume is that? So you can directly convert it and get your information that I have so many meter cubes of water inside. And you can see the sensor there with a stainless steel sensor assembly and a stainless steel diaphragm or a ceramic diaphragm at the bottom. The pressure acts from the bottom there, and the instrument directly measures and gives you a signal that is proportional to the water level in the tank. So this is another alternative way. There are many other, for want of time, of course, we cannot look into each and every. There is bubbler, and there are other ways of measuring level as well. We will look at what is more relevant, economical, cost effective, appropriate for our applications now in current times. So that's level measurement for you. And the next parameter that in the water industry that we measure is pressure. Pressure is a very, very critical parameter in a water network, because Many times you open the tap where you live and the water is coming in a very narrow, thin stream. And that's because the network, the pressure is very low. So you want to be able to measure the pressure and maintain sufficient pressure there so that, when from the water network, your sump is getting filled or you're getting water, wherever you're getting, there is sufficient pressure available. And of course, throughout your network, you will have pressure drops. So, and depending on consumption upstream, as you go further and further away to the tail end of a water network, the pressure drop can create problem and it can create non-availability of water. So for this online, you can use pressure measurement, in association with computerized systems like SCADA, etc. You can measure the pressure and say this is 4 bars, 6 bars, 2 bars in a water network, the pressure, and you can have a local display for any operator who would be passing by, and you can also send a signal to a central control room using very conventional, the last item there, it says 4 to 20 milliamps, 2-wire output. Now that is the most basic standard way of transmitting signal from a sensor. Of course, you can have more advanced communication technologies, etc., from the sensor itself. So 4 to 20 milliamp is a typical simple pressure measurement device, which you can then wire it into an Internet of Things IoT or a remote telemetry unit, to send data to a central system or to store data in a data. All of this is possible. So it is an important parameter, with levels increase pressure, at least in the farthest points in the network. Now, one other thing that, in terms of measuring pressure is if there is a breakage in pipe somewhere, you will have a telltale evidence, which is loss of pressure. So if you are monitoring pressure in your water network, then between 2 points, if you notice a pressure drop, then means you could imply that there is a broken pipe somewhere in this area. So this is why pressure is quite extensively monitored in water networks. Now, some of you may be familiar with these basics, but since there is a varied audience, I'm having touched on some basic issues in terms of measurement. So I hope if you are familiar, please bear with me. For the sake of others, let's go through some of the basics as well. Now, 4 to 20 milliamps, 2-wire output. That means that you are on a 24-volt DC power supply or a 12-volt DC, something like that. Now, these are good if, when you have a DC supply, because you can use solar power, for instance, where you don't have mains power supply available. If you are in the middle of a city and you can get a power connection from the electricity agency, that's great. You can put up your measurement device on mains power. Otherwise, you may need to use alternative like solar power, for instance, or batteries. Then 12-volt DC, these kind of systems on 4 to 20 milliamp make it much more maintainable for you. Now, there's something that's mentioned here, HART communication, that is highway addressable remote transmission. That is a way of sending data from the meter to a remote system. That's an American protocol, not widely used in our country. Just to let you know that there are things like HART, Modbus, or Profibus, or some de facto standard. Now, one thing, ladies and gentlemen, what I would like to say, anytime you buy an instrument, please make sure that the inputs that come in and the outputs that go from the instrument are in some standard, internationally recognized protocol or signal type. What that means is then later when you use that signal, you can connect it with any system. If you use some odd type of signal which others do not support, then later if you want to make any upgrade or any change, you will be stuck because your measurement devices are in a non-standard category. So in any infrastructure upgrade, which is a serious subject in our country, infrastructure upgrades, this standardization in terms of power supply, in terms of communication, in terms of the type of signal, the type of enclosure you use, the standardization is very important. So that's on pressure measurement. Now let's move to the next, which is an incredibly critical performance for water performance parameter, is flow. Now there are many ways of measuring water flow, and that depends on whether the top picture that you are seeing, you are having a water flowing in a pipe. Now that pipe can be full of water or it can be partially full. Do have water flowing in channels, like irrigation canals, for instance, or there are parts of treatment plants which operate on open channel. And of course, you do have other water bodies like rivers, things like that. And you need to be able to measure. You need technology to measure in various of these conditions. Now, the most commonly used two technologies are electromagnetic and ultrasonic again. So these electromagnetic and ultrasonic are the most commonly used ones, and hence they would require some clear consideration and analysis. There are other methods like overflow weir, V-notch weir, or flumes, partial flumes, etc., where you actually maintain a structure which varies the level but keeps the velocity constant in any open channel flow. So then by measuring the level, you are able to compute the volume. That is a very economical way of measuring water flow, and that is deployed often in treatment plant inlets, wastewater treatment plant inlet and outlet, and these kinds of situations. We use weirs and flumes and things like that. But nowadays, much better, much more accurate measurement is possible under ultrasound technology. You can measure partial pipe, you can measure open channel. So these things need to be carefully considered so that you can select sensors suitable for your application. Then, of course, there is the highest frequency gigahertz range radar measurement, which actually in a water that's flowing, you can use it to measure the surface velocity. This radar is something that policemen use in for speed guns to catch overspeeding vehicles and things like that. So the same can be used also to measure. It is used for surface velocity measurement. So you can measure water flow very accurately in irrigation canals and things like that. Wastewater flow in a sewer system, etc. These are all possible with radar technology. Now, a bit more closely into one or two of the other technologies. One is ultrasonic. Now, ultrasonic flow measurement. Flow, for measuring flow at all, what you are actually measuring is velocity. At what velocity is the water flowing? That could be in meters per second, for example. How many meters does the water flow in a second? You can have, and in water networks, in municipal water systems, typically you have velocity ranging from 0.2 to 1 meter per second for velocity, and that's normally in our usage, we find that kind of velocity. So you have to measure the velocity and convert that velocity into volume flow. So if you are in a condition where the pipe is flowing full, then the entire pipe diameter, the cross-section area of the pipe, and you calculate the instrument will calculate for you the volume flow and give you directly in a unit of your choice, whether liter per second or cubic meters per hour. Water, of course, is measured in volume, but certain other chemicals, if you look at petrochemical, for example, oil or fuel or some such, then that is gravimetric measurement. It is measured by weight. Water, of course, everywhere, even your water billing at home happens based on units, which are cubic meters. 1,000 liters of water makes 1 unit. So to measure in volume, you want to know the velocity and then the cross-sectional area of the pipe or the channel that is carrying it. And ultrasonic measurement, as you see in the picture, and as per ISO 6416, as we say here, it is done by two sensors. They send signal to each other. One sensor sends with the flow direction, another one sends a signal against the flow direction. What the instrument does is find out how much, when the ultrasound signal goes with the flow direction, it will face an acceleration. And when the ultrasound signal comes against the flow direction, it will face a deceleration. So there will be a difference in time. So if it takes 10 milliseconds to travel in one direction, it might take 12 milliseconds to travel in another. So this 2 milliseconds difference in time actually corresponds to a specific velocity of flow. So with that velocity, you are able to compute the volume flow. That is how you use ultrasonic to measure flows. Now, of course, you can also measure the velocity of a flow based on some particles embedded. If it is raw water and you got some sand or particles in the water, then these suspended particles can be tracked. You look at the position and you look at the same particle after so many milliseconds, how much it has traveled. And thus, the instrument works out the velocity for you. And the standard, international standard ISO 18769 is one that governs this kind of Doppler, or what we call cross correlation measurement. We can look a bit more detailed into it as we move forward. So these are ultrasonic measurement solutions. And of course, in the water industry, which I'm sure that most of you would be familiar, is electromagnetic flow measurement. Now, here the measurement happens because water is electrically conductive, and it is made to travel in a magnetizing field. Material travels in a magnetizing field as per Faraday's law that some of you may be remembering. It induces a potential, an EMF, electromotive force, within the water, and that is measured by electrodes. So you will have an electrode there which is measuring how much EMF is generated when the water moves in the pipeline. So obviously, as the velocity increases, the EMF generated will be more, and it is able to calculate the volume flow. Now, one very, very important consideration here is that you need to make sure that the pipe is full. Electromagnetic flow meters do not work under partially filled pipe condition. And also, as you are depending on an electromagnetic induction here, you need to have certain minimum flow velocity. For example, 0.5 meter per second. Generally, you do have some who make meters to a lower velocity. But electromagnetic meters work efficiently when the velocity is 0.5 meter per second. So if you are having networks, we have seen water networks where the velocity can be very, very low, 0.2, 0.3 meter per second. In such cases, if you try to put electromagnetic flow meter, then obviously your accuracy will not be there at all. So if you have velocities, it's much, much better to go for ultrasonic flow measurement, which can go even up to 0.01 meter per second. It will give you the specified performance accuracy. So these are all various types of flow measurement devices. Let's move on. Yeah, we've been looking at the sensor technology in terms of ultrasonics, and in this slide you are seeing what are the options you are having. Now, here you need to consider your situation. Am I in a pipe which I can cut and put a meter that can go inline? So I get a very economical, for example, Boltzmann type or a mechanical water meter that I can put inline. That is one option. Am I able to isolate the flow, cut it, or drill the pipe to put a sensor? If the answer is no, then you may have to put a sensor that does not intervene into the pipeline. That is the second one that you see, which is a clamp-on sensor. The sensor can be fitted on top of the pipe outside, externally, and from there it can travel and the ultrasound signal can go and measure the velocity in the pipe. Now, there is the Doppler cross correlation measurement system, which we discussed earlier, which is about looking at objects, entering particles in the medium, in water, and seeing how they travel and what is the distance they travel so that you can use that velocity measurement into volume flow calculation. That's the cross correlation technology. You have the technology that is suitable for open rivers, which are wide, very wide rivers, like the white ball sensor that's there. That is that normally carries like a 500 kilohertz crystal sensor, low frequency crystal. Otherwise, typically these open channel meters go up to 1 megahertz crystal sensor, and in gigahertz range if you are using radar for surface measurement. So these are all the different sensor technologies. And you also have, if you are measuring at the inlet to a water treatment plant, what you have at the bottom there, like a wedge sensor. You install the sensor at the bottom of the channel, and then it is looking up and measuring the velocity and the height of flow in the channel. And then from velocity and the depth, it can calculate the volume flow directly for you. So these are all there is a wide range of sensor technology. The reason I wanted to show this to you is you may face water flow, use electromagnetic. Electromagnetic is a very rugged, robust, long-lasting device, but it is not suitable for all applications. As we discussed, it's not suitable for very low velocities. Sometimes you have to drop the pipe diameter. If you are, for example, you want to measure in a 300 dia pipe, you may reduce the diameter to 200 to make sure that the pipe is full of water. Now the trouble is, the moment you reduce the diameter of the pipe, you have created a pressure drop in the system. And that pressure drop will always remain throughout the life of the system. So what you want is, depending on your water condition, whether it is in a wastewater treatment plant, whether it's raw water, clean water, dirty water, sewage, municipal wastewater, what have you, drinking water, river water, you want to measure it in the condition that the water is. You don't want to change the condition or adapt it for measurement. So that will give you a continuous cost drain, energy drain, if you try to adjust your process for measurement. Much better is to adjust your measurement to suit the process, the process that is happening. So from the sensors, water, the signal normally goes to a transmitter RTU device, like the one that you are seeing here. It has got its own display. All the wires get terminated on those green terminals in the front, and it is reading data from the sensors and storing them internally. And it can send the data out to an intelligent data transmission device, which may be using your telecom system and sending information outside. And later from that device, you see something, the SCADA telemetry system. Some of you may be familiar with what is SCADA. SCADA means supervisory control and data acquisition. That is, you are able to control the process from remote. You are able to start and stop a pump, for example, or set at what pressure or what level the pump should be operating. That is supervisory control. And then acquiring the data. I mean, what is the discharge pressure of the pump? What is the flow rate from the pump station? What has the flow rate been for the last 1 day, 1 week, 1 month, 1 year? So this is all acquiring and storing data. That's a SCADA system functionality. And nowadays you use telecom services to bring the data together. There are also other communication protocols available, which is a very vast subject in itself. We can have some discussion in the end, time permitting. If you have any questions or inputs into this, we'll come back to that later. Let's move on. This is how, at the outset we discussed about how an electromagnetic flow meter is working, and I mentioned that it operates based on Faraday's law. You see in this slide that if you look at the slide down below, you see a colored line which is magnetizing coil. This magnetizing coil sends a magnetic field through the pipe, and when the water flows through the pipe, this magnetic field induces an EMF into the water. So with electrodes from two directions, you get to measure the velocity of water that is flowing here and then convert it into volume data. Now, of course, the thing to note here, as we discussed earlier, is that the velocity of flow should be above a minimum cutoff, for example, 0.5 meter per second. Above that, the meter will work efficiently. Otherwise, it does not induce an EMF accurately at very low velocity, and hence the meter accuracy suffers considerably. Accuracies vary from 0.5 to 1%, and once this is working, it can be a very, very rugged, robust measurement device, electromagnetic flow meter, long-lasting device as well. But the trick is to make sure that magnetic flow meters are deployed only where it matters, not everywhere. It's not a one-size-fits-all type of a solution. So please be careful in selecting where you put the sensor, because we see many cases where people go and specify, oh, water measurement, magnetic flow meter. And then later you find that the meters are not functional. So please, if you get the opportunity, select the meters to work for the process that you have, and don't try to adapt the process to your measurement scenario. So that is how an electromagnetic flow meter is working, and here are some typical visuals of magnetic flow meter, where you have this flanged construction which goes into the pipeline face to face with the companion flanges. It sits in the pipeline, and then of course there is the electronics which does the signal conditioning and sends the data to a central system if required, or it can just sit there and keep the data within and show you a display locally. So that is how an electromagnetic flow meter is working typically. Yeah, this is again, look at how technically it is working. There is a magnetic field and there is an EMF induced. When a conducting medium like water flows in the magnetic field, that EMF is measured and directly converted into velocity, and that velocity is converted into volume flow. So if you have good velocity, like above 1 meter per second, the magnetic flow meters give excellent accuracy and they give good 15, 20 years life performance mostly, and those are very robust solutions that you can have. But the trouble is, please watch when you are selecting your meter, make sure that you don't deploy something which is not applicable for your process condition. The ultrasonic flow signal for clean water application is called a transit time measurement system, where if you see the picture here, one sensor sends a pulse to the next one, and then the system is calculating how much time it took, how many milliseconds did the signal take to travel from sensor A to sensor B. Then B gives a signal in the reverse direction. Then the system looks at how much time it takes for the ultrasound signal to travel from B to A. Now, one will be with the flow direction and the other will be against the flow direction. That is what gives you the differential velocity, and from the velocity you compute the volume flow through the pipeline. That is transit time method of measurement, which is very commonly used in water application. Now, what is shown here is a clamp-on sensor. Now, the clamp-on sensor, of course, in our industry, there is concern in our country, especially that the sensor may get stolen. If you are clamping something in a way that it can be removed, then somebody will be interested in a little bit of copper or some such that is part of the cable or the sensor, and they may cut and steal the devices. That is a limitation, but there are ways to manage that. You can hide the sensor, protect it quite well, so that it's not easily available or visible to people who are looking for vandalism and things like that. So this is transit time velocity measurement solution. ISO 6416 is the standard that governs this. You can have a read at the standard. How does it work and how to calibrate the instrument, etc. And this kind of device can work more or less for any medium at any, that is 0.01 to up to 20 meter per second velocity, which is way above anything that we will look at for water system. This is the typical solution in terms of clean water flow measurement. And hence, of course, you can have these solutions in different configurations. You can have these solutions with a clamp-on sensor where the sensor is fixed outside the pipeline, sending a sound signal through the pipe material. Or alternatively, the sensors can be fixed within the pipe. And then you bring the cable out and take your data out. That is internal, inside pipe installation. And thirdly, you can have looking at the pipe from outside, inserting a sensor. Now, why would you want to insert a sensor into a pipeline? You don't want to disturb the water supply in the pipeline. So online, you can hot tap on the pipeline, drill an opening, insert the sensor, and acquire the data. So these are all the various types of transit time meters that we are seeing. On the right hand side, you see how they show the measurement in a canal situation, where you are measuring the velocity with these sensors, and you are measuring the depth of measurement through either an embedded sensor along with the the velocity sensor, or a separate level depth monitoring sensor. So all of these are shown at the bottom as well, showing once again how you can have varied technologies, varied sensor configurations that are available for you to acquire your water data. What are the advantages of this technology? The first and foremost, now we have calibrated these meters in the Fluid Control Research Institute, very close to where we are. Now, we've got accuracies in the range of 0.2 to 0.3%, which is as good as it comes in the water industry. So very high accuracy measurement, and it is difficult to achieve with conventional flow meters. And another thing with conventional flow meters, as we discussed earlier, is the velocity, where you need a certain minimum velocity, and it doesn't work well at lower velocity. The third thing is by having these multiple paths. See, in this photograph there, you are looking at a sensor which has got 8 sensors there. And these 8 sensors operate, if you are able to see the blue lines that are crisscrossing inside. These 8 paths operate as individual paths. So effectively, you are having these 4 paths which are measuring the velocity, and then what the instrument does is it averages after measuring velocity in 4 different directions within a section of the pipe, and then it says what is the average velocity, and then based on the pipeline inside parameters, the diameter of the pipe or some such, then you can calculate, the system will calculate the volume flow for you. Now, the beauty with this kind of technology is that you can install it without shutting down the pipe. This is a very important. If you can install the sensor without shutting down a water network, sometimes in projects you have to say, oh, this water that comes in from outside. In Mumbai, we are having pipes. The largest one is 3 meters diameter that brings in water to the city. So you have to measure the velocity in a 3 meter diameter. That's a huge pipe. The biggest that we have done in India is 6 meter diameter pipe. That is at the inlet to a hydroelectric power station in a pen stop. So the technology, why I mentioned 6 meters. 6 meters is a huge diameter, and you can actually measure the velocity in various configurations, multi-path or single path, depending on the accuracy you require. You can get excellent measurement results here. So this technology is easy to install. All you need is to weld a nozzle, which put a ball valve there if required, and then insert the sensor through the ball valve. So it can go there and establish itself and give you the performance accuracy. Even if there is some sedimentation or something happens inside the pipe, there will be sufficient signal and the meter will work very well with these parameters. So that is ultrasonic measurement system, high accuracy, ability to measure very low velocity. As we said earlier, that electromagnetic flow meters can measure up to 5 meter per second, 0.5 up to 1 meter per second, I'm sorry. Whereas ultrasonic flow meters can go even up to 10 meter per second from as low as 0.01 meter per second. Very high accuracy, velocity measurement system. So these are some of the advantages of the transit time metering technology. Let's move on. Now, you see here the different accuracy levels when you use the instrument in a single path or a multi-path, normally under installed condition. If the pipe is partially full, then you get an accuracy of about 2%. In open channel, you get about 4% accuracy. In a single path system, single path means 2 sensors only, not multiple sensors installed in a pipeline. Now, as the number of paths increases, you will notice that 2 paths, 4 paths, 8 paths. You notice that there is a very significant increase in accuracy. 0.4, 0.2 meter per second at the highest, and up to 2 meter per second at the lowest. So you are able to get excellent velocity measurement by increasing the number of measurement paths in your system. And of course, earlier the cross correlation sensor. Here in this slide, you are able to see embedded particles. Like you have raw water coming from a river. Then you have some suspended sand or some pebbles or some embedded particles, sometimes some biological life that comes. This device is able to track the movement of specific particles and then see how much the particle traveled at a specific time period. So the particle is traveling with the velocity of the pipe. So by measuring the particle velocity, it is able to compute the pipe velocity. Now this is the Doppler measurement system, which can also become a cross correlation sensor. What is the difference there? Is if you are measuring the velocity based on one object, then you are looking at a point velocity, and the measurement that you are having from a single point, some single suspended solid. It may not be the average velocity in your pipe. What you want is what is the inner diameter and what is the average velocity in your pipe. So that is the cross correlation technology as well, that can be used for raw water, not very clean water, raw water, natural water, or river discharges and these kinds of things. We have used in many cases for wastewater systems this kind of technology. Now, for the sensors that are available, you will see the sensors in a sleeping arrangement, like a wedge. The wedge has got two sensors. You will see a couple of dots on the sensor. The one at the bottom is depth sensor. How much water is there? It will send an ultrasound signal from bottom to top. And then it will measure the velocity as well that is flowing in the pipeline and calculate the volume flow. Now, these are all on the left hand side. You are having these sensors which are looking at open channel measurement system, and you are having the sensor on the right hand side which can be inserted into a pipeline. So if you want to measure water flow in a pipeline without stopping the flow, this is the sort of device that you can consider using. Now you also see in the top here various combinations of electronics. That is a transmitter there which receives the sensor cabling, the sensor signals, and then you can program the device and generate the output signals as you require. And there are multiple formats supported by these devices, from conventional 4 to 20 milliamps to HART or Modbus communication protocol and things like that. So depending on your specific requirement, you can select the solution that you want. And another interesting thing is these boxes here. These are portable devices right there in the middle. So it has got internal double batteries inside, two batteries in one device. So it gives you good battery life. You can recharge one battery and replace it on the run. So you don't have to take the device out. If you want to measure at a location without power supply, you can use this wonderful device. It will measure and store the data, and you can come and remove it as and when. So that's a portable device. And on the right hand side is an insertion device, which is again a 4 to 20 milliamp signal output device from tank, discharge, etc. These are this is the cross correlation technology and how it takes the velocity. Now one important point, how this averaging Doppler, what we call cross correlation, how it works. You see in the bottom right hand corner, you see these zones, windows, window 1, window 2, window 3, window 4 to 16. So you have specific areas above the sensor. The sensor itself is located at the bottom of the pipe. And then the entire pipe is divided into 16 zones. And then it takes a velocity measurement in each of these zones. And then averages out the velocity and gives you very good record of average flow measurement using. So this is a very economical option. Of course, there are various different options to bring data from raw water systems. But suffice it to say that it is a very simple, easy to use, easy to install and maintain device, the cross correlation sensor. Now, I am running along here. I hope it is okay. If you have any observations or anything specifically that you want to talk about, you can put questions in here, and we will respond in the end. And I hope it is not, because I'm not getting any feedback. I do not know about the audibility, etc. So if you have any problem, kindly do let me know so that we can regroup and continue the session. Now, moving on, we saw the ultrasound signal and the cross correlation signal, and this is the radar device. Now, radar technology is very well advanced now. Recently, I installed some sensors in irrigation canals in Gujarat. These measure the surface velocity of water quite well, and then it also measures the depth of water flow. Then, knowing the velocity and the depth, you can calculate the volume flow quite efficiently. The photograph there is a device. It says EX there. It means that it is suitable for the hazardous area, which is in a wastewater system, in a sewer system. Normally, these are used also for sewer monitoring. We will see that in great detail in tomorrow's session, but it suffices to say now that it gives you good measurement for clean water as well as for wastewater application. And why is wastewater critical now? In our country, we are actually reusing wastewater, as the industry experience. Of course, you would know how the reuse of wastewater is being planned, at least initiated in our country now. So if you can measure it, quantify it, treat it, then it can be a great big asset for the country which is deficient in water. So this is a radar-based device, how it is deployed, with a velocity and depth sensor, etc. Actually, this is a combination meter which deploys the contact type cross correlation technology and the non-contact, something that sits outside water, the radar sensor. It's a combination of two different sensing mechanisms, which is typically used in combined sewer overflows and things like that, which is, we will look at it more closely in wastewater applications tomorrow. So these are all the varieties of sensor technologies that are available for you for water. Now, what you are seeing there, the slide, there's a photograph of an irrigation canal on the right hand side. I'd like to point that out, and we have put our metering device right there on the bridge. You see a bridge there across the water. We install the velocity and the depth sensor from the bridge and calculate the volume of water that's going through the canal. So these are all very intricate, tricky ways of accounting for water. When you give water for irrigation, how do you account for it? How much water has been consumed each day? Most of the water resource in our country is going for farming, for agriculture. So it is important to make sure that every farm is getting sufficient water, and that is possible only by proper measurement. Otherwise, it's a hit and miss. Some days you give water, some days you don't, depending on what is happening before it reaches a particular farmer. So this is how technology can be deployed for getting information from irrigation canals, and this way you account for every bit of water that comes out of nature, and then measure it and use it judiciously, control the measurement and the entire water transmission and distribution process. This is what allows you to do. Speaking of technology, now we move from sensor technology to how to acquire the data, how to control from remote. We'll take a look at some of the possibilities there. Nowadays, the monitoring and control systems are very much web-enabled or web architecture system, which makes it very, very easy. You don't. There were days some 30 years back where you would need a control room to measure and manage. You need operators to sit and look at the process from where they are and take decision. Nowadays, the mobile phone that you are holding in your hand can be a source of information from your water network. Now, if you are, for instance, a water treatment plant supplier, then what is the reflux rate? How is the efficiency of my plant? I put some metering equipment for that. Then this figure can come to you continuously, and you can see how your plant is behaving. What is the quality of the raw water that my plant is, groundwater that the plant is receiving? For example, the groundwater is having a lot of TDS or suspended solids, and that has an impact on your plant productivity and performance. All of these can be monitored in very reliable web-based systems, and you can store the data, analyze, and it helps you to take decisions. Uh, Now, the software that you use for monitoring and managing what we call a SCADA, supervisory control and data acquisition system. Nowadays, like hardware, the software also comes in a very modular fashion, give you exactly what you require. Oh, when you are having a monitoring and control system for a city, like we are doing a project for the city of Chittoor in Kerala, and we're doing a project for our Mumbai city there. What you do is how many meters are there, how much data is coming in, and what are the specific details of each meter. These things are all controlled in a manager module. Typically, the name might vary, but manager module, as the name implies, it keeps control over the various aspects. And the device module is helping you to configure. Oh, I have a flow meter here. I have a level sensor for the overhead tank. You have the inlet and outlet flows for the OHT. That is done by device management module. And then you have abnormal conditions in any water network operation. Like you can have low pressure, you can have high flow, you can have low level in a storage tank or a very high level and overflow from a storage tank. All of these are alarm considerations which tell us to go and do something. When something is not right, then you got to go and maintain. So you have the alarm capability, and then very importantly, the analytics module. Analytics means to analyze the data. If you are having the raw water that is coming into your water treatment plant, then the water that is going out from the plant, and you have some losses in the plant itself. Then further downstream, your bulk water system, it is going into overhead tanks. So from your bulk water source, from the treatment plant to the overhead system, that may be several kilometers of pipeline in which you will be losing water. What is the loss in that part of the network? And then from the overhead tank downstream, you have a distribution. We'll see it in more in detail. So up to the local areas where your consumer connections are up in that area, what are the losses you are having, and then finally up to the consumer in a particular area. If I'm taking 1,000 cubic meters of water a day, how much is actually reaching the consumer and how much is getting wasted along the way, lost due to leakage, losses, etc. So that's analytics. So the software, system software itself has got these various modules which help you to define and achieve your monitoring and control objectives. And of course, you have the visualization, which makes it more interesting. We have done some visualizations using GIS maps, for instance. There are many ways of looking at information, make it user friendly. Then you can have charts and other bar graphs and things, which is indicating a trend. What is the water consumption increasing or decreasing? From winter to summer, is the consumption increasing? These are all indicated possibly as in a graphical way, which is called the chart module. And of course, you can also schedule your maintenance. So some systems, not all of them, but some systems do provide you facilities to manage your maintenance. So for example, you got to maintain a pump, lubricate it once every 6 months. So you can set up a schedule in the system which will send you a warning. Oh, it is 6 months. More or less like servicing our cars, I suppose, that you get a warning and then you go to the service center. So like that, it allows you to schedule your maintenance and keep up the efficiency of your plant. Let's move on. Ramya, just help me if you could. Are the attendees seeing slide number 26?
Yes.
Here, and am I reasonably audible here?
Yes.
Could you please confirm that?
Yes.
Yeah, both are yes. That's great. So we continue. So these are all the various aspects in a modern software-driven SCADA monitoring system. And of course, you have reporting, which, what is my water consumption this week in metering area number? Is my water consumption in another area? What is my per capita water consumption? These are all aspects of reporting, analysis and reporting. And then transfer of files in various formats, even to the business environment. You may remember the very first slide that we looked at. We saw a model from the sensor into communication, and communication to the control center to the IT environment, and then upward into the analysis and business environment. So whether I have to upgrade a particular facility, is my water network overloaded now? Do I have capacity for another 100 connections? These kinds of things can be available directly online, where instead of waiting for people to come with information can be configured to be readily available. That's the modern way of managing water system. And there are a lot of communication protocols. Again, that itself is a subject. The control devices that you have in a water treatment plant, for example, or a pump station like a PLC, you can have from various manufacturers with the different types of signals, uh, different purposes, flow, level, pressure, analog signals, digital signals, pump vibration monitoring or control of variable frequency drives. So these are all possible with various communication protocols. Now, one thing that I would like to point out to everyone attending here is please make sure that you select, if you are using any system, that you select one which follows some international established standards. because if you get lost in a vendor specific communication system, then you're always locked with that one vendor. So whereas if you are using a Modbus protocol or a DNP3 protocol, DNP is something that's widely used in power systems. So if you are taking open solutions like MQTT is a modern teletransfer protocol, it is very light in terms of, so the data transfer efficiency and the accuracy, the disparity, accuracy checks are all very good, and so you get good reliable data almost on a continuous mode in modern like 4G 3G systems. So these kinds of, you have to select solutions including the sensors, the communication technology, and then the data management solutions that are applicable for your application, is the point that I'm trying to make here. And of course, you can analyze the data in graphical ways. This is showing different parameters. A flow that could be going up and down, with diurnal variations and things like that. A pressure drop suddenly in a water network, which is indicating a burst pipe condition. And you can see that all on a timeline. Oh, this happened at 9 o'clock in the morning. So, and you can correlate with, how this pressure drop also resulted in an increase in velocity. So it helps you to correlate and understand your water network and manage it in a very user-friendly, powerful way. That's what technology allows us to do. And of course, you have the alarm management. In terms of examples, you can say real-time information, like high flow, low pressure, very high level in a storage tank. These are all alarm. And when you are doing the metering, if the meter has lost power supply, for example, that also could be an alarm condition, saying that so.
Mr. Prakash? Hello? Okay, sorry about the inconvenience, boss. Mr. Prakash is facing a little internet connection and he's back.
Yeah, I'm back now. Sorry about that. And so we were
I
looking
think
at
so. We missed out
alarm.
on slide 30 itself.
Yeah, we are on slide 30 right now, and we're looking at
31.
alarm conditions. We have discussed that at length earlier, where the idea is to look at abnormalities, high velocity, low pressure, high pressure. All these conditions can be identified and listed with color coding, so that something critical is wrong or something routine problem in a water network. So these SCADA systems, computerized systems, give you ability, and also it gives you direct SMS or email or voice messages, so that you can receive communication. Somebody operator who is far away can get an information that your overhead tank air is overflowing, the water supply got disrupted or something. So these are the features of SCADA systems, and the systems allow you to go for very, very reliable monitoring systems. You can have dual redundant servers, for example. In fact, multi-redundant, not even dual. You can have very robust, reliable hardware configuration and 100% viewing in a web-based solution with graphical system. The screens here typically water treatment plant with an aeration system or a settlement tank. Then you have the rotating arm in the settlement tank that needs to be controlled. So you are able to see the various aspects, the activated sludge pumping or the screw pumps that are there for removing the grit. These all the devices in the plant can be monitored and managed from a central location. All the operations can be automated. So, if you are having screens, for example, based on, we saw earlier that you can have a differential level based control of the screens in a plant. Means that the plant will run by itself. You don't need manual intervention at all for operating. We just need to apply the right sensor technology, define our requirements well, and then it can be implemented. Nowadays, because in our country as well, a lot more wastewater treatment plants are being specified, be SCADA enabled, and to have capabilities like these. But what is important is not only to have these solutions, but to have the people who can handle them. So the operators are trained in handling it. Solutions like these training programs are useful in that respect, that not only senior managers can come and see what the industry can provide for them, but even the operation staff, they can see how to use the technology and how to make the technology work for them. Now, another very interesting area where we are working on now, it's very new in our industry that we are applying. In water networks, municipal water systems, a lot of water meters are existing, mechanical water meters, which have been in operation for many years. Now, there are efforts in many towns to replace the old mechanical meters with what they call AMR, automatic meter reading systems, where the metered data is periodically communicated to the central server. And then you have a billing application that runs there, and the bills can be generated and transmitted to the consumer, and they can even pay digitally, electronically from where they are. So this whole process of acquiring consumption of each and every consumer from their meter to generating the bill and then accounting for the payment can be digitized and integrated into system. Now, the project that we are doing now, it has got a billing application where the bills are generated for the customer, and then it also serves a lot of analysis. What is your revenue water, for example? In every area, each consumer has got a certain water consumption in the billing cycle. So once the bill is generated, you add up all the consumption in the area, then you say, okay, in this particular ward or in this particular metering area, this is the water consumption. and then you can look at per capita water consumption there. Now, one other very interesting aspect is, instead of replacing thousands of mechanical water meters, which have served reasonably well over the decades, you have these POS devices, point of sale devices, which is, the picture shows here a handheld device like a laptop. So you go to your old mechanical meter and take a reading, as it has always been. Somebody comes there from the water department and he enters the current consumption, and immediately the bill for the consumer can be printed out and given right then and there to the consumer. And the measured data is automatically updated to a central server. So now, without replacing tens of thousands of water meters, simply with a bunch of handheld devices, one per meter reader, a town can typically have 20, 30 meter reading people. If each one of them is carrying a handheld device like this, he will be able to go to the consumer and enter the meter reading currently, and that information will get stored in a server, and it will help you to analyze your revenue water in great detail for each area. So this is a very, very cost effective way of digitizing without changing your metering, etc. This is where availability of simple technology like a POS device can make a big impact in a country like ours, where you don't want to, or you are not able to spend a lot of money for high-end metering solutions. Sometimes you can still depend on the simple age-old mechanical meter and acquire the data, digitize, and improve your management of the resource quite conveniently. This is a dimension that I wanted to present to you. Perhaps you see potential for use like this. In fact, quite recently, in the last week, there were a couple of interesting things that happened. The Central Groundwater Board made a statement that they want each and every user of groundwater to meter and have telemetry solutions. So the groundwater metering should be available with the ability to transfer data, so that somebody is able to track at some level how much groundwater is being tapped. And this is particularly relevant in cities which are heavily dependent on groundwater in the summer months, like the city of Chennai, for example, where you are having a lot of groundwater usage and it needs to be managed efficiently. Now, another thing that has happened is the commercial consumers. The commercial consumers are asked to go to digital metering systems, so that, for example, 70% of your water consumed may be with 30% of the consumers. So if you meter this 30% of the consumer well, and if you make sure that they don't waste a lot of water, then that considerably improves the 70% of your total consumption. So this is where technology is coming into play. Chennai Smart City, they have asked all the uh, commercial users to switch to AMR metering systems. There is a very, very nominal cost that has to be incurred for the AMR meter, but in terms of the availability of data and then the lack of abuse of water resource, it's money well spent, and great improvement to the water network which we are all seeking. Now, for some people who are, for example, an RO plant seller, it might be very useful to have the meter in your plant, which can be read directly into your mobile phone. That is possible now, so that you know how your plant is behaving day after day. Very, very simple, nominal, low cost metering can bring you useful information on efficiency of your system. That's what I mean by revenue tracking here. And one other thing, when this is something that I use while addressing municipalities and all who go for individual consumer metering with these AMR meters, etc. Now, a municipality which was hardly having any metering to begin with now switches to several thousand meters that all need to be maintained. So, your systems have to be maintenance friendly. So, if a meter is not sending you data for 24 hours, for example, then you could generate a warning that this particular meter is not responding. It could be a meter failure or it could be a power failure at the metering location. So you got to see when a device is healthy or you are having a problem, what is the volume, when was the last data given to you. All these things can be readily available so that you know that all your meters are working. And what is more important is if you have 4, 5, 10, 15 meters which are not working, you are able to spot it and rectify it quickly instead of having to search around in multiple locations saying which are my meters which are not working. The system can come out and tell you, look, these 20 meters are not operational. You better go and check these. So that user friendly can systems be. And of course this is all a bit repetitive in terms of a bulk water meter. Also the domestic water meter can give you reports. You can have a mobile phone where each municipal consumer, if you have a water meter at your house, you in your mobile phone you can have an app which helps you to track your own water consumption. So if your pipe has cracked and you are losing water somewhere over time, your mobile phone will tell you without the intervention of the water department, look, my consumption has increased, I need to do something about it. So this kind of technology is available for our use in the water industry. I think we can skip these. These are all visualizations which we have already covered. You can have tabular record of data or a graphical one. You can compare the previous month with the current month. These are all what we are doing, in water networks. For every consumer, how much did he consume last month? How much did he consume this month? If there is parity between the two, then okay, it is normal. If, yeah, next one. So this is what we had mentioned earlier about the mobile app, where you can look at your own water consumption. You are in a municipal water system which has got, I don't know, thousands of water meters, but you are able to track your own water meter through your mobile with a simple app. And you can say how much was it yesterday, how much is it today, how much was it last month against this month. All these kinds of analysis is possible using a mobile application. So in a water network, it improves the efficiency of the consumer by himself, and it also helps the municipal corporation or the water distribution agency to analyze how much each one is consuming and who is wasting more water, etc. All this information can be made available. All this analytics can be made online, visible. NRW assessments. Now we will look at how the non-revenue water can be assessed in a water network. You see, water, NRW means water that is taken from the source and yet it did not reach the targeted destination. Means the water is getting lost somewhere. Many times in our country, we face problem because no one knows where the water network is. Oh, I think that pipe is on the right hand side of the road, 1.5 meters from the road edge. You're not too sure. There are old pipes, there are new pipes which are laid above. There is a spaghetti of pipes under the ground and you don't know which one is operational. And oh, the people who knew have retired, and the new people who have come in, they have a learning process. They will take years to familiarize themselves with the water network. because all the available information has been lost. Now, one thing that we would like to suggest for municipal corporations, which again is happening in one of my projects, is a GPR study. GPR study is a ground penetrating radar which helps you to identify all the major pipes which are below ground. The supply source pipes, the bulk water transmission and distribution pipes, and then the local, in each area there are 100 dia, 80 dia, uh, 110 dia, 150 dia pipes which are distributing water in each area. All these pipes and pipe material can be identified and recorded very accurately. The locations can be identified. You can put them in a system where it is available for you readily. If you are losing water in a particular area, at least you know where your water network is. So you have a good chance of doing something about the losses. So these are all very cost-effective ways of obtaining asset data that is below ground. And of course, if you have assets that are above ground, a GIS study, you can do drone-based mapping nowadays, which helps you to record your infrastructure very, very accurately. So these are very cost-effective ways of digitizing and establishing your asset infrastructure where it is. All these pipes that have gone in over the years, different pipe materials that are there below the ground. You can have all the interconnections and the valve chambers and everything identified and all the records available so that you go from people dependency to system dependency. So this is something that I would like to recommend very heavily for the water industry. Please record and know where the assets are so that you can manage them. And that digital information leads to the transformation that's required. This is how, that's the case of GPR study, how a device is used to penetrate the ground with radar signals and then identify the infrastructure that is there. And this is all mapped. And in the end, the final result is you get CAD files like DWG, AutoCAD files, which are showing all your pipes that are below ground. So, and that's a very, very cost effective way. Typically you could measure, you could verify at 25 or 50-meter intervals the pipe and then sketch it all together and your water network will come up there. All the as-built information will be available. So a very, very worthy progress for any water network. This is typically a CAD file on a water network. So this is pipes below the road, as you can see. There's the road and you see what it is showing is a proposed meter location in the water network to measure how much water is going. Everything that is a circle is a meter location. And you see all the pipes that are identified, where in the road they are. Can you imagine without this system, how would people know who are maintaining it? Somebody who has come up and taken over maintenance. How would they ever know where their pipes are, where they are leaking, where there is a pilferage from the system? How would they know? Except by doing a study like this. Now, how do we analyze the losses in a water system? We start from the source, measure how much water is coming from the source, how much is coming to the water treatment plant, how much is leaving the treatment plant. And the differential there is the losses in the plant itself. And then once the water leaves the treatment plant, you have the bulk transmission, which is going into your bulk storage and then on to your overhead storage tank and distribution, the transmission distribution system. So this is the area transmission losses, bulk water losses in your system. And then from there on to the distribution. Sorry, the network is playing some small games here and there. So we do have the local areas where you have the overhead storage tank or a below ground storage reservoir. You measure the inflows into that. That way, layer by layer in your water network, all the way up to your consumer metering, or you can have a smart domestic meter, or as we said, use a point of sale handheld device to record from an existing old water meter how much your consumption is. Now, if you look at the same thing from bottom upwards, you first of all at the lowest level, you are deciding how much is my revenue water, how much water has reached my consumer in the last month or 2 months on your billing cycle. Then how much has been distributed into each area, how much has been transmitted in the next level up, then how much water has come from the plant and how much water has come from the source. So these, all of these can be totaled up online automatically, and for the user you will see a picture area wise, metering area wise. You can look at what are my consumptions and what are my losses, which are my efficient areas and which are the areas where I'm not accounting well for the water consumption. All of this can be identified using SCADA type solution. And remember also one thing, the type of meter you use, also it can be very, very customized for your condition, for the town, depending on the pipe material, the pipe location, etc. And in the next slide, we will see how to efficiently install the bulk water meter. We can skip this one. And yeah, next one. Let's go to the installation now, because otherwise we won't have a lot of time left for questions. What we need here, do we have the installations slide? Yeah, we are coming to that. I think what we need is accurate, reliable measurement system which will last the lifetime. We don't want instruments that will work for very, very short duration and then fail. We want the years of operation. We want the online analysis to be available, and you want systems driven water management, not depending entirely on people driven solutions. This is how we transition from the old ways of doing things into a modern efficient water management system. Of course, we have to bear in mind that in our water networks, the networks are old, and in many cases the pipes are getting replaced, but not always. So you have to live with the old pipes, how to efficiently measure and manage. Now, of course, there are installation considerations. What happened to the installation? Technical challenges when it comes to water metering and monitoring, etc. You will face different pipe materials in your network. These are all things that actually, it's a quick recap of what we have been looking at. Now, on the right hand side, the graph you see is actually from a city, the water consumption in the bulk water systems. Where the velocity in the water network in the old pipes is below zero point 0.3 meter per second, mostly 0.2 to 0.3 meter per second is the water consumption velocity. So you can imagine that you have to deploy measurement technology that can handle these low velocities. Otherwise, you may put a meter and the meter will sit there and look good, but it will not give you any useful data, because when the water is flowing at 0.2 meter per second, this device will sit there and think that there is no water flowing at all, or the accuracy levels will be compromised on. Then if you want to install metering, are you able to isolate the pipe? Are you able to cut the pipe and put inline meter? Or do you need an alternative solution which can be installed without having to cut Ramya spoke about our project for the city of Mumbai early. There, it is the mandate by the municipal corporation there is to provide metering without isolating the network at all. We cannot go to the municipality and say, can you shut down this pipe? I want to install a meter. With them, all the meters have to be installed with very, very high accuracy measurement, completely online. Even pipes that are as large as 3 meters to the smallest pipe, which are, I think, 300 mm in that. So all these pipes, you have to install the meters without without shutting the pipe. So how that is done is by insertion technology. We drill a hole and insert the sensor, hot tap it into the pipeline. So whether it is a new pipe or an old pipe, it doesn't matter. We are able to penetrate that and install the meter and get very, very high accuracy data. So this is how you would need to monitor in, major cities are thinking like this, that I don't want to specify meters and then someone comes in, but I'm not able to give him a shutdown of the water network, so the meter cannot be installed. That too has happened in our country. So there is a wide range of flow velocities and varying hydraulic conditions in the pipeline. We should be able to handle all of these. You should be able to handle the different piping materials. The more you are aware, if you were a municipal engineer, the more you are aware and you are able to specify, the more cost effective your metering solutions can be. You see, we talked about cutting and installing a meter in a pipeline. This, for instance, is an electromagnetic flow meter that is typically installed in a water pipeline. So if it is a half meter or a 1 meter dia pipe, you can imagine how much time it would take and effort it will take to isolate, because the valves in the network may not hold. You have to isolate the network, then you have to cut the pipe, put the flanges, install the meter, then hook it all up and commission again. This would be days, if not weeks, of work. Whereas alternatively, you could have a metering which is clamped onto the pipeline directly without any intervention, or you could drill a hole and insert into the pipeline uh, and get equally accurate measurement solution like the one that you are seeing here on the left hand side. A single point insertion into the pipeline can give you the measurement, or with certain types of materials of pipe, a clamp on sensor as well can give you very good results, measurement, and the installation will take only a matter of 1 hour or some such, very, very easy to install. So if a city wants to install meters and they've got 60, 80, 100, 200 meters that they want to install, and if each meter installation is going to take several days, you can imagine the time that will be taken before you have the metered data available. Now, if you use your sensor technology well and select it and use the right technology, you will be able to do multiple meters in a day. So it means that in a month, you might have 40, 50, 60 meters installed up and running. So an entire city metering can be made to happen in a matter of months, not years that it could otherwise take. These are all considerations to think about when selecting the approach to take. Normally, if you have to provide metering, what do? You survey the area, and then you say, okay, now I have to construct a chamber, or how do I have to install the meter? How do I get access to the pipeline? What metering do I provide? All of this, the metering comes in the tail end after you have made the chambers and all. Now, in modern times, whereas in old cases, your metering may come up in month number 10, it begins in month number 10 after you have started thinking about metering. Whereas now, with the clamp on technology and all this, once you know where to put the meters, very early, as early as the second or third month of the project, your metering installations can begin. It means that all the 6 or 8 months of metered data will be available for you to manage your water network. And 6 or 8 months of measured data may actually justify your project budget almost entirely for, because in any water improvement project, if you want to look at cost, the metering cost would be about 5% max of the entire network asset cost. So at less than 5% cost, your payback period can be very, very low. If you are smart with it, you can keep the cost down and you can bring your meters early enough. And in the months or years of data that you get early, that will justify the metering cost entirely. So this is just a quick analysis of cost and time and how to bring about a smart approach in providing metering in your water system. And this one here, it looks at different technologies from a cost perspective. The two main technologies that we are looking at is electromagnetic and ultrasonic technology. Both are quite reliable. Electromagnetic, of course, is a very, very robust metering solution. And in terms of cost, you will find that up until you are measuring in pipe sizes which are, say, 300, 400 mm or less, electromagnetic flow meters is very efficient, cost effective, accurate. But as the size increases, the ultrasonic meters become very, very cost effective. The thing is with ultrasonic measurement that the same sensor can measure in different pipe sizes. So your cost is more or less the same, whether you are putting a meter in a 300 dia pipe or a 3-meter dia pipe. Your cost of meter installation is more or less the same. That is why you see when it comes to ultrasonics, a straight line on cost. At some point, the electromagnetic flow meter can be less expensive, and at some point it gets much higher. So if you go from 300 mm up to 1 meter dia pipe, the ultrasonic flow meter becomes much more economical for measuring. And then the time involved also, you see a very significant increase with size. Ultrasonic flow meters can be deployed very quickly in any pipeline with minimum labor and time involvement. Whereas electromagnetic flow meters, because you have to shut down, isolate, cut the pipe, etc., it is a lot more time consuming. And here is another in modern water metering, because many of our cities, they want to do metering. They come out with a bid to provide metering, and they say for each and every meter you have to construct a metering chamber. So if you have a project that comes out with, I don't know, there was one with the 2000 meters, and they're saying each meter has to be provided with a metering chamber where the sensors can be installed. Okay, so now all of a sudden a metering project has become a civil works project. Construct 2000 chambers in public areas. So you got to have the required permits in place without disrupting traffic and things like that. So the construction part becomes very laborious, time consuming, approval oriented, and expensive. Whereas by using the ultrasound technology, we looked at the clamp-on metering. You are able to install the sensor, cover it off, which is what we have done in this particular installation with a part of a conduit, and then fill it up with foam so that the sensors are fully sealed, Remember our discussion earlier that the sensor can be IP68, ingress protected to IP68, means that even if it is submerged in water, nothing will happen. It will not get damaged. It will continue to operate. So you close it out like this and then backfill the excavation. The pipe is below ground pipe, as you see. Now, if you backfill the excavation with sand, then you have saved the cost of constructing these expensive chambers. Each chamber cost 30, 40, 50,000 in Indian rupee terms. All these costs and the time can be saved by deploying the right technique and the right way of protecting the sensor. This is why the installation method for any instrument becomes very, very important, because a lot of the country's resources can be drained out making metering chambers, which later, for those of you who are familiar with metering chambers, I'm sure you would have seen that these chambers are homes for reptiles and home for water logging in your infrastructure, and that brings about corrosion of valves and things like that. Now, for metering, at least, there is no need to construct such chambers. You can do it very, very effectively and bury it off. And if there is any need for maintenance annually or so, all you have to do is come with a spade, remove the sand out, do your maintenance, fill it back again. So these are all lessons that we can learn here in doing large scale city-wide metering schemes, etc. Now, this is from our project for the city of Mumbai, how in a very large pipe, I think that's a 2.2 meter dia pipe, where we are marking exactly, if you start looking from the top left to right, we are marking the distances on the pipe, and then you see the crosshair there, which is where the sensors will go in, and then you weld a nozzle and a ball valve on the pipeline, and then the sensor goes in through the nozzle and ball valve and gets inserted. Now, the bottom left hand side, that is a ready, fully installed sensor, and nobody has disturbed the water supply even for a minute. So this is how, a lot of time and effort, economical, efficient metering with early availability of data can be possible. And that is a pressure insertion tool that is being deployed. The water is under 4 bar pressure in that line, and we are inserting the sensor, in a like a tool that looks like a jack of a car. We just turn the handle slowly, the sensor will go in place and it will settle down, and then you remove the tool and lock up the sensor where it is. That's the picture on the right hand side there, a sensor that is happy, ready to function, installed. So this is how you install your metering without disturbing your water networks at all, even in very large pipes. Now, some of the automation strategies we can have a quick look at. I hope that's okay, that Ramya, that we can take a few more minutes to. We've already done nearly 2.5 hours of time in this session. So I would like to take a quick look at the automation technology.
We can give about last half an hour to 45 minutes for Q&A. So
Yeah. I think we will wrap up in the next 10 minutes or so.
Yeah, not
and then leave the field open for discussions, questions and answers.
That's right. All
okay,
right.
Thank you. So in any water treatment plant, one area that requires automation is your sand filter system. Normally the treated water gets filtered in. Wastewater plants are different. We will look at it in a lot more detail tomorrow. In water treatment systems, the sand filters, they are the final filtration element in the water treatment process. And you have the water is coming in through a pipe, and then it is falling on the filter bed, and it gets drained out, the filtered water from the bottom. And what you have to do is, because the dirt will settle down on the sand bed, and then it will start to block the sand bed, the level will build up in the filter and you will not get production from the filter. So then what you do is a process called backwash. If you are from the water industry, I'm sure that you are aware of this process itself, where you actually put water from the reverse direction, pressure water from the bottom, so that the dirt will come up from the top, and you drain out what we call the supernatant. The dirty water can be removed from the top. And then to disengage the dirt from the sand, you also use what you call scouring air system. Now, this whole process of, from the time that you close the inlet of a sand filter to allow the water to drain out, and then close the filter discharge, then allow the water to come in from the bottom, which is the backwash water. And once the backwash water comes up, the dirt that comes out from the top, to drain it out. And then you have a scouring air cycle where you put, along with water, air from the bottom, compressed air from the bottom, that disengages more dirt from the sand. And then again you drain it out, then put the filter back in service, open the inlet, again open the discharge, and the filter is back in operation. Now, if this whole sequence is done manually, it can be a very inefficient system, because either you may backwash the filter too frequently or too infrequently. That both would mean that you are operating under less than optimum production level. So it is possible to see when the level is building up in the sand filter using a simple, for example, ultrasonic level sensing system. And as the level starts to come up because the filter bed is blocked, you start a backwash cycle. And in a water treatment plant where you have 15, 16 sand filters, for instance, you will not backwash them all simultaneously. So you could go cyclically, 1, 2, 3, 4, 5, do an entire backwash cycle, one filter to another. So there is an automatic process for backwashing one sand filter. Then once that is completed, the sequence can jump to the next one, and then to the third and the fourth. Like that, you continue and you completely backwash your entire system. That is quite often in our country, that is a very manual process, but that is something that can be very easily, efficiently automated. That is one part in a water treatment plant where the efficiency can come. Now, other parameters, of course, when you are sending treated water out to customers, you have to monitor certain parameters. So what is the inflow and what is the outflow from the plant, for example? And then depending on the treatment process, you have other measurements. But largely, look at the water quality that is going out. What is the turbidity of the water in nephelometric turbidity unit? In other words, how clear is the water after your treatment? Then dissolved solids, that is the salt content, the conductivity of your water, to make sure that you are not giving saline water. What is the pH of the water? In other words, that it is pH neutral, as close as possible. And finally, that you leave a residual of chlorine by dosing chlorine gas or chlorine, that is hypochlorite, in the system. You leave a residual in the system and you measure and record that I am having a specific residual chlorine in the system. And of course, one automation that happens in any plant is for the chlorination, where the chlorination is a factor of the residual chlorine concentration on one hand and the flow rate on the other. These two parameters combine to automate your chlorine addition, so that you don't either give excess chlorine or deficient chlorine. So the bacteria are well and truly destroyed and the water is disinfected. So these are all some of the water quality monitoring parameters. Sometimes, of course, there are a lot of other parameters that are specified for online monitoring, but it is debatable whether you need much more than that online. The other parameters which are slow changing, they can actually be analyzed in a laboratory. So these are the essential bare minimum plans that the monitoring that you can have in a water treatment plant. The automation will evolve around the sand filters in any water treatment facility. So we have talked now. Thank you for the patience, first of all. We have had the time to talk through water networks, different techniques, cost effectiveness in metering, how to select specific meter for your specific application, then how to build city-wide schemes, then how to integrate into computerized systems like SCADA or some other, call it a smart utility management solution, how to integrate all that together, then how to assess the non-revenue water in your system, from starting from how much is revenue water and then how much is lost and where exactly the losses are, how to systematically provide a metering solution that will lead you to an assessment there, how to use handheld meters, POS devices, uh, to utilize even existing old mechanical meters and acquire online data from them. And another important point that I would like to reiterate as we close the presentation is how a GPS study can help the water infrastructure to be recorded accurately, so that the, the maintenance of your system becomes at all possible. We simply as a nation, I don't think we can afford to live in that innocence of water management where there are losses. There is water from nature. We take more and we lose more. That innocence now may not do. We would have to move to excellence in water management. How are we going to transition from this innocence to excellence in water management using monitoring and control technologies that are available? That has been our subject of discussion. I hope we have focused in the right areas, instead of losing too much breath on this communication protocol and that PLC modules and things. I have tried to focus on what matters in the real world. Now, thank you very much for your patient listening, ladies and gentlemen. Now, I'll be happy to listen to any questions that you have. Ramya, if you want to open up the free part, which is data acquisition and remote control. These are aspects that we have, the technical specifications of a data acquisition system. What are the things that you need to look for? You have a software solution, it means you have to have an operating system, and then it has to be an open system that is maintainable, something that you can use and carry forward as we do any IT platform, something that can give you information into other, your normal desktop computing systems. So that is from a server specification point of view. And then, of course, nowadays everything is web architecture. Means that whatever you can do from a control room, you can also do from your mobile phone that you are carrying around. So accessing the system from remote for duly authorized people, not for everyone. So these kinds of features are part of the system now. There are cities with multiple wastewater treatment plants, for example, or pumping stations, etc. So if you build a computerized system for automating operation and then monitoring and management of that, then the same operations team can manage all the STPs. Some of the STPs can even be unmanned full time. You can be monitoring all of them. And even when the operator is traveling from one plant to the other, he can have a mobile phone which is telling him what is happening in any of the plant. So these kinds of technology is available for use now. And these are things that we have looked at, the communication protocol. Suffice it to say that when you are integrating a system with multiple sensors or multiple wastewater pumping stations or treatment plants, make sure that the data exchange happens through some established, proven industrial standard communication protocol. That could be anyone, but it should be a standard one with multiple vendors are supporting. Otherwise, you may end up, in extreme dependency on single vendors, etc. Data analysis we have looked at yesterday. What are the flows? What are the variations? And what is the pressure in the system? Or, and what time is your manhole surcharging? All of these can be very graphically analyzed. Alarms, events, reports, SMS or email communication, all of this is possible. Whatever is required for your wastewater system. If you are a wastewater plant supplier, then you may have multiple wastewater plants running. You can automate them, or you can give yourself a monitoring solution. It's simple, cost effective, and allows you to keep an eye on all your plants. If you are an STP, private STP operator in the city of Bangalore, for example, and you are operating 100 wastewater treatment plants, you can provide yourself a centralized system where you can see what is happening in all of these plants, and then you can minimize the people. The very idea of using technology is to minimize the need for manual intervention, and that can be very effectively achieved now. Reporting, we have looked at these things yesterday. I don't want to repeat what we discussed yesterday. If anyone has a question, we can review at the end of the session. We can have a discussion on that. Now, reliable monitoring. Nowadays, you don't want anything that is not web-based. You should have information flowing freely from your monitoring system out into the mobile domain, where you can feel control over your infrastructure assets wherever you are, and you are able to centralize the monitoring of your plants into one system, and then have very nice visualizations. As you see on the right hand side, you can create screens like this which tells you what each and every equipment is doing, how many hours your screw pump has operated. So if there is any maintenance due, you can plan for that. These systematic operation and maintenance practices can be established using these systems, and you can do things which are event driven, because the events are available, known, noticed, and recorded. You can be controlling things based on an event. When you are monitoring and you are having surcharges every day at a specified hour, and you know when your peak flow is coming, and you can think of a way of handling that. These are again slides in terms of cost effectiveness. What type of meter to use where, if you were, I showed you the example in Paris, where there are three pipes of 3 meters diameter. And if you were to install an electromagnetic flow meter in each one of them, then your cost would be, in our rupee terms, it could be in excess of 3 crores possibly to get it installed. Now, the same measurement is being done through 1.5-inch nozzles on each pipe, and the overall cost of installation by comparison could be in the range of 30 lakhs. So these are the kind of commercial considerations, comparisons that we would say you need to take into consideration. First of all, asking what is the technology available for this? What are the challenges that I will have if I have to provide measurement in wastewater system? Then how to overcome that? What is the equipment? Vendors will come and tell us, oh, here is what I make. You use it. You can reduce. If you think there will be partial pipe flow, then reduce the pipe diameter. Then what happens when you reduce the pipe diameter? You get a pressure drop across that. Not only for a day or two, but for the life of the system, we have created a restriction and a pressure drop by reducing the pipe diameter. Now you have technology available which ensures that you don't have to do such things. You can measure, you can have a full bore pipe, you can just go on doing your piping and then come and fit your metering later. These are the things to bear in mind, when you think of putting up measurement devices. So what will we do? A simple way of measuring is you can make a small tapping, as we discussed a while back, a small 1.5-inch nozzle, insert a sensor through that, connect the wire to the transmitter unit, mount the transmitter somewhere on the wall, and away you go. The data is available for you. So the installation process can be so simple, cost effective, and user friendly. Saving time, protecting the environment, safety considerations, etc. Is there a question? Yeah, we see a question from Mr. Rajendra Kumar Jayachandran. We can use it in effluent water plant at chemical industries. Yes, sir. Excellent question. Actually, you can use these instruments in effluent treatment plants in the chemical industries. Only thing is you will have corrosive chemicals, possibly chemicals that can react with your sensor construction. So we take some special precautions, while using in the process industry, knowing the condition of your water. If there is any risk of acid flow and these sort of things, then chemically resistant material is used for sensor construction. Now, for example, Teflon, PTFE, that's a material with very good chemical resistance. Sensors can be made with PTFE construction, which gives you very good life in industrial environment. Yes, to answer your question, yes, it has been very widely used in effluent treatment plants, and it can give you excellent performance without any problem. Only thing is the sensor material has to be carefully considered. So I hope that answers your question. Anything else that anyone would like to discuss before we go into the last part of our presentation, which is which part of a wastewater treatment plant do we want to automate? I'm just waiting to see if there are any more further questions.
Yeah, I have once again Sagaran from Vapi Industrial Effluent Treatment Plant.
Yes, sir.
Is there any color interference will be there, because the effluent is having different color at different times? Will there be any issue on this matter? No.
No, it is not. The color will interfere in optical systems.
Okay.
These are not optical at all. If you are measuring turbidity in an optical instrument, then the color can have an interference. But since these are not optical, these are high frequency ultrasound signals, color will absolutely have zero impact.
Okay. In the monitoring also, I like to have process parameters like oxygen, BOD, COD, TOC, pH, ammonia, nitrate. Whether that will also be integrated in this? Can it be done?
As a general thumb rule, what I would like to suggest to you is there are certain parameters which are sensors are available for all the parameters that you just mentioned. Nitrate, ammonia, these things may matter in certain specific areas. Like, if you are in textile industry area, then you have certain type of pollutant that you want to monitor. Not everywhere. So if you are talking about municipal wastewater, not industrial wastewater, then a lot of these parameters need not be monitored online. They can be, analyzed on a periodic basis, daily or some such.
Sorry to interrupt you. Ours is an industrial effluent coming from different type of industries, and this is a common effluent treatment plant of 55 mlt capacity. It varies color, parameter, different parameters are varying.
Right.
So
right.
We are interested in that. That's why I asked.
Yes, you could well be. I mean, the answer like what I gave you, it cannot be generalized for all conditions. Now,
right.
What is applicable in your area may not be applicable in another area. It depends on. There are places where there are a lot of tanneries, for example, and there is the textile industry domination, or there is a petrochemical industry in some places, or some places it's a mixed bag. So by analyzing the water repeatedly, you know what kind of pollutants to expect and at what frequency. If there is some occasional discharge, then do you want to monitor for that online 24/7? Because it is very easy to set up these monitoring systems, but then the monitoring process itself, it could be an electrochemical process, for example, with electrodes and things like this. They will keep running out, and you have to keep replacing them, because the more you add complicated monitoring systems, the more you must have a budget for maintaining them. They may serve a purpose, but it depends on how frequently you have a pollution and at what concentration. Something like US EPA, Environment Protection Agency, there are some regulations, guidelines for what is the type of monitoring required. They could be used as a guide. And if you are having, my water contains so and so too much of nitrates, for example, then it is good to monitor for nitrate, but you need not monitor for each and every parameter that are there. The idea is to draw the line between what you want to measure continuously and what you want to measure periodically. Now, the periodic measurement you can even do with, nowadays you get these portable sondes, which is a bunch of sensors which you can carry to site and dip it in the manhole, and you can say what are the various parameters that you have. So even if you don't want continuous online monitoring, the BOD is something. For example, if you are not having serious BOD issues, many major wastewater treatment plants in the world are operating without online BOD measurement. Then you have the labs which carry out the analysis periodically. Another way is you have these refrigerated sampling units, which every hour they connect. I have done systems where these samplers are kept and they collect a sample and keep it in a refrigerated environment in bottles. Then at the beginning of the day, you can take these bottles away, and these samples are with a label, 9 o'clock, 10 o'clock, 11 o'clock, or whatever frequency you are setting. And then you can take these away and analyze in a lab. Now, why not online? The only consideration is cost. If you have project budgets also is not a big deal actually. The problem is in having to maintain all these instruments and making sure that they continue to work for you. So my suggestion is please optimize what you want to monitor online. Turbidity, for instance, is a good parameter for treated water. pH is an excellent parameter. Total dissolved solids is a very good parameter to monitor for wastewater. When you are sending it out for reuse, then residual chlorine is an important consideration. So these are all parameters that I would say they must be monitored. Other than that, what do you want to monitor at the STP inlet? Do I want to know the biological oxygen demand or some other nitrates and other metals and things like that? That is a call that needs to be taken specifically for your plant, not generally. So, shall we move on to the next part then?
Yeah, I think you can proceed.
Automation strategies for wastewater treatment plants. See, here are some of the graphics. I've put up the images here so that we can see, the important aspects of this is an extended aeration wastewater treatment plant. So normally, what do you have at the inlet to a wastewater treatment plant? You might have a lifting station where you want to monitor the level there and make sure that you are not building up the level and overflowing, etc. at the inlet. So level monitoring and control for pumping stations which are feeding into the STP might be the first point of consideration in terms of automation. Now, TDS monitoring. TDS monitoring for wastewater in many countries, it is widely used where the groundwater is saline. Now, a lot of my work was done in the Middle East, where they do have groundwater, but it is very, very saline groundwater. So, if there is groundwater ingress into your wastewater system through, through damaged sewers, etc., then TDS gives you the story. If I've seen the TDS going above 10,000 ppm, then it is a concern that there is external ingress into your wastewater, considerable amount of external ingress. TDS can be conductivity or salinity, as we call it, can be a good indication of what is coming in from outside. Then, as you enter the treatment plant, your first equipment is the screen, the bar screen, the mechanical screening equipment, where you want to remove the screenings periodically on timer. A lot of the treatment plants in our country, they sit with manual removal of screening, which is not very efficient at all. You can have screening removal periodically that can be automated based on time. And of course, you can have a differential level system. I think we saw that in an earlier slide, where you look at the water level upstream and downstream of the screen. And if the differential level increases, it means that the screen is blocked. And then you automatically remove the screening. So the screening operation can thus be optimized. So that we also see, I've seen in our busy metropolitan cities that the screen gets blocked and some kilometers away, very close to the airport, in the heart of the city, you are having wastewater coming onto the streets. Why? Because the HTP screen, the screenings have not been removed and it is blocked, and the manhole is, that happens when you have treatment systems which are of, where the capacity is fully utilized. So automation of the screening and grit removal systems on time and on parameter like level would be a very useful addition to a sewage treatment process. Now, the next is your settlement tanks, whether it is before the aeration or after. You have the sludge, uh, the solids settling down at the bottom. And one very useful area, and it is a bit problematic as well, is the blanket level, sludge blanket level control. So if the sludge blanket at the bottom comes up too high, then you are not using the capacity of the plant. Or if it is too low, then you have risk of water running off with the sludge, and your sludge system gets overloaded. So to run the sludge removal system at the correct level, whether it is primary settlement or secondary or tertiary, as the case may be, the sludge blanket measurement devices can be very handy. Now, the other is the most important aspect in a conventional wastewater treatment system is dissolved oxygen based aeration control. So in an aeration system, you are either using blowers or blowers with diffusers or agitators to aerate the wastewater. And excessive oxygen means excessive use of energy. So you want to make the right amount of oxygen level for the biological life to sustain. And you can do it very, very effectively with the dissolved oxygen sensors in your aeration lane. Nowadays, you have very robust and reliable technology for DO measurement, and that can control your aeration speed. If you could use even variable frequency drive for your blower or the agitator that you are having in the aeration lane, you can make your entire aeration very, very energy efficient. And that is the most energy consuming part of your sewage treatment plant. Then activated sludge, as you go in after the aeration lane, the sludge that is removed from the settlement tank, it splits into two. One part of it is returned to the aeration lane with the biological life, and the other part, the surplus, is wasted into the sludge removal system, maybe through thickeners or through a digestion process and dewatering. The sludge gets removed. So how much sludge to return? What would be the optimum amount? How much to remove? That can be based on the water flow into your aeration lane. It can be proportional to the incoming wastewater flow to the aeration lane. That is an excellent control as well, because it helps you to optimum bacteria level in the aeration lane. And as we looked at for water treatment plant, the sand filter stream is a very good area for automation, because it has got, when you have lots of sand filters lined up, 16, 18, 20 odd sand filters lined up in a big plant, backwash them is a big task. So to do them sequentially so that you can operate the plant with minimum number of scouring air blowers, optimally drain the system, because if too many sand filters are backwashing simultaneously, then the drains will be overloaded. So everything can be automized by sequentially backwashing the sand filters. You go for one filter at a time, control the duration of the backwash, make sure that the levels are optimum in your system. Make sure that when one tank is going into backwash, that other tanks are available to take the additional inflow. So these processes can be completely automated, and it will stabilize your plant performance considerably with that. Then, of course, the treated water quality we talked about a while back, TDS, pH, turbidity, residual chlorine. These are to be monitored. I think must be monitored in any wastewater treatment plant discharge, particularly going for reuse of the wastewater. Then, of course, looking at the sludge side, when the sludge is going for thickening or digestion or dewatering, the feed into the system can be automatic with adjustable flow rates. Depending on the sludge volumes that are being produced, if you have multiple dewatering centrifuges, for example, you could distribute the flow equitably to the dewatering centrifuges so that neither of them is overloaded. The plant will continue in a steady state operation system. And last but not the least, of course, chlorine dosing control. That is a very important parameter to make sure that your water is disinfected but not excessively chlorinated, both from a safety and cost point of view. So the chlorine dosing you can have, the control normally is based on the water flow coming into the dosing tank as well as the residual chlorine concentration at the discharge. So that is a parameter as well that can be automated. So then you can also look at things like the sludge removal from the settlement tanks, which can be either continuous mode or a batch mode, where you use timers. Now, all of the functions that we have talked about, they can be done with SCADA or PLC, programmable logic controller type concept, where the devices, the PLCs, can remain in the area. So you keep the wiring to a minimum, keep the controlling device very nearby, and then you network them all and connect it with the central computer system server in the control room, so that you can sit there and monitor and manage everything. And you can minimize the cost of cabling that you do for monitoring and automation purposes. So your plant can have multiple PLCs sitting here and there, and then all integrated into a central monitoring platform. So this is in terms of wastewater systems, and of course for for the sewer systems also, you can have a SCADA type solution where you monitor all your pumping stations, each and every pump operation, and see whether any pump has failed or there is a power failure here or there. What is the capacity in your sewer system? So if you are putting some flow meters in your gravity sewers, you are able to see whether your sewer is overloaded or not. So if your treatment plant has got a failure and you're not available for some hours, how much water can your sewer system hold? These kinds of operational considerations can all become very, very visible instead of getting hidden below the ground. So this overall as a strategy for wastewater treatment and the wastewater networks monitoring and management, they appear to be two independent activities, with possibly some level of interaction, in the sense that the final pumping station, how much water is getting pumped to the STP is something that you want to know and keep it steady as far as possible. Other than that, these are entirely two different operational systems as in practice. So that is some operation strategies for you for sewage treatment plant. Of course, you have small treatment plants as well, like MBRs and things like that. That will be small capacity. And nowadays, you could even residential apartment complexes and things, they have compact sewage treatment units which work to various levels of success. And if you are operating multiple of these plants, then you do have the option of putting up a display monitoring system which cuts across all these plants. Then if I have to monitor 20 treatment plants in a city, All of them can be monitored and managed. And also from a compliance point of view, nowadays, environment agencies insist that you retain some information. What are you discharging? How much are you treating? All these information might need to be retained and made available, and in cases sent on a regular basis to the pollution control board system. All of this is not only possible but very viable today with the open technologies that are available. So that is the end of our presentation on wastewater, and indeed our 2-day training session on potable water management as well as wastewater management. I trust that that some of these would have been revealing, or you have got some information that you might want to deploy. We could open up some more questions before we conclude the session.
Good evening, sir. Once again, Sagaran from WAPI.
Yeah.
I just like to have a few queries on automation. On the valve control position and automatic control of the valve, of the flow meter or chemical dosing, all those things are possible. This is one aspect. Another is these equipments, instruments, or otherwise the monitoring facilities and control facilities, is it available indigenous or it should be imported? Any maintenance spare availability in India? And the third point is this automatically statistical analysis of this data over a hourly or weekly, shift wise, and daily, monthly, and yearly, and it is to be control on the statistical parameters also.
Right.
Do you have anything on that front, sir?
Yes. I can comment individually on the points, and I may need your help to recollect because you've lined up 3 questions in one. The first one is when you try to control, then position feedback of your controlling device, how to maintain it in that position and make sure that you are able to achieve steady state operation. That seemed to be the first angle that you were addressing. Now, my suggestion is the most simple way is to operate in a batch mode rather than a continuous mode. What that means is, for example, in every half an hour, you open a gate for 5 minutes and close it. Instead of trying to keep the gate open 20%, for instance, and then you are depending on the gate feedback. And if that feedback fails, then you don't know what is happening with your control. So if you have the choice, then what I would recommend is you operate in batch mode of operation, where you set your time duration and you can have control over the timer. For example, you say that removal of sludge from a settlement tank, I want to remove for 10 minutes every half an hour. I'm just giving some random number. Now, it can be made available in your control room. So if you want to change this from 10 to 15, then you can change it. And you can even develop strategies like during the times of peak flow, I want to increase the desludging in my settlement tank. And then during the night time, I want to reduce the desludging from the tank to, maybe once every hour, for instance. So this kind of strategy and operating on time instead of operating on percentage open might be a more maintenance friendly approach. That is the question number 1 that you gave. Number 2 is what is available indigenously in terms of monitoring. Now, one thing that I can tell you is in terms of quality, water quality monitoring. If you have parameters, like even simple parameters like pH measurement devices are available in our country. They are fairly economical. But many of them say, no, I can't give you any guarantee for my sensor. So the electronics is okay, that we do very well. But the sensor technology with the glass electrode or the membrane and whatnot, those are not perfected, and manufacturers do not give you warranty for that. So in these electrochemical processes, how much life will you get out of these sensors when you buy them indigenously is a very debatable point. And if you don't get warranty, then you might as well buy from a source that gives you, the reasonable, at least a 1 year warranty type of thing. So the problem that we have in our country is in terms of sensor technology. The electronics is pretty good, but the sensor technology still has got rough edges to be improved. If that answers the question on the analysis. The third part is the data analytics that you were referring to. Data analytics in terms of what happened last week, what has been the performance on a weekly basis, on a monthly basis, what is the pattern in the summer months, what is the pattern in the winter months. All of these are very important aspects. Now, if you put a reasonable SCADA solution in place or a distributed control system in place, nowadays the technology allows you to do all of this kind of data storage and retrieval and analytics online without any difficulty. Certainly possible. One thing to watch for is when you develop computer systems, obviously you need people who can handle software. And the limitation comes because these are coding people, they do not understand wastewater or water. So they will provide, from their limited perception, some reporting. It is very important beforehand, if you are going to initiate a project that I want a SCADA system with all these analytics, I want to know what is happening weekly, monthly, annually. I want to monitor these parameters. What are the inflows? What are the outflows? How much treated effluent am I generating? What is my water quality? A lot of data is there. Your idea as an owner and an operator is that this data has to become information. And this information is generated from data by an IT technician who doesn't understand the information. So it is very important to have people who are familiar with both sides of the spectrum. At least you need to know, and you need to tell it in your specification. This is what I want in terms of reporting. I want so many reports. I want weekly on this parameter, monthly on all of this. If you define, then you engage a specialist contractor to come and do a SCADA system for you. He will have no choice but to sit and understand and provide the information for you. But if you say provide a SCADA system with HMI, blah, 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 graphics, reports, alarm strengths, without defining what you want the system to do, then they will do what is bare minimum, and give you a solution that will do your job, but it will not do what a system can do for you in modern parlance. And many times we don't plan to do a further upgrade or an improvement or some more analytics into the system. In our industry, in the water industry, we don't invest in that sort of thing. So if you want to bring solutions, please write down in detail what you want to, or engage someone who can actually write these things for you, and then make sure that they get coded and you say, oh, now I want to see a report that says this. When you see it in front of your eyes, yes, that does the job for you. So it all comes to predefining what we require, and then it can be. So these were the three aspects that I recollect.
It's a good thing you are thrown in the right direction, and I also understand this. And we keep communicating, and I think we'll be able to proceed further on the implementation of these technologies in upcoming projects in our plant.
Mhm.
So I would request your contact numbers and all. I'll get it from our Water Today that training program.
Yeah, it is
Yes,
actually
but the training's content, that is the slides, would be emailed to all the attendees. And the first slide has Mr. Prakash's email and contact number. You
Okay.
can get in touch with him with that.
Okay,
But in
fine,
case
ma'am.
if there's
Thank you.
anything, you can get in touch with Water today, and we will help you get in touch with him.
Right, right. Yeah.
you, you
Thank you.
you
Thank you
see
very
on
much.
your
This is a good
screen.
information.
You
Thank you.
see on your screen now my email ID and contact number. I'm happy to assist you as I can with your requirements, and feel free to write to me. Uh, so that's a very nice. I've enjoyed the presentation, good interaction. Some questions which are coming with good understanding of the business need. So thank you for being with the presentation today, and it's been a good
Any
couple of
more
evenings.
questions?
Uh, yeah, if there are any more questions, I'm happy to take that from any of the attendees. So if there aren't any more questions, then Ramya ji, what I would like to do is to thank you very much for these interesting sessions and the interaction, and thank all the
There is a
attendees.
there is a question, Mr. Prakash.
Okay,
Hold on.
thank
There
you.
is a question.
That's
We
great.
have Sapna. She requested for mic access, so I'm just giving her the mic access. And Sapna, kindly go ahead with your question. Please unmute your mic. Yep,
Hello?
Sapna, please go ahead.
Yeah. No, I have some problem. Means I was not available yesterday. So can I get a whole presentation copy for 2 days via email?
That is something that Ramya ji can answer for you.
Yeah, Sapna, you will get the content at the end of the session.
Yes,
You
with
shall
training
receive it by
certificate
email.
also, no?
Yes.
Yes, okay. Okay, thank you, sir. Thank you, sir, for presentation.
Thank you very much indeed. I have enjoyed the presentation. These are very interesting and pertinent subjects for our country. And going 15 years back, nobody would have sat around to talk about monitoring and automation and these kinds of things in our country. These were not relevant subjects, but water situation in our country is driving us to take these things seriously. So all of you who are having some impact or the other in the water industry, I would humbly request you to take monitoring and automation as a serious subject, deploy the right technology and deploy the right systems. And if we continue as we started yesterday, we said if we continue to do whatever we have been doing all these years, then the results also will continue to be what they were. We got to perhaps change the way we do things, improve, deploy technology, leverage it for your operational benefit. And so I wish you all well. Stay safe. I think we are getting to the tail end of a problematic period with this COVID virus. I wish you all well, and stay safe. And any more queries, feel free to contact me, or through Water Today. I'm happy to address you. And once again, Ramya ji, thank you very much for having me on board in this session. And all the very best to everyone. I'm concluding my session here.
Thank you, Mr. Prakash Madhuswamy. That was a good session. I request if anybody else who's got questions to kindly request for mic access, or you can post your questions in the questions section. We'll wait for a couple of minutes. Meanwhile, I would like to thank Mr. Prakash Muthuswamy once again for taking time out and making such a detailed presentation. Although we have very few participants in this session, we'll definitely, but I'm sure and I trust that with whatever that you have provided, with all the information, your presentation proves to be a lot of information and details. And I guess you have covered a lot, which is why I think the details were so informative and that the questions are very few.
So indeed, we have tried to look at things from not so much from a theoretical, but from a practical user point of view. What to deploy where, what is available in the world for me to do what I have to do in the wastewater domain. That's how we have tried to view the presentation. And yeah, if there's anything more, I think we can conclude the session here, and of course any queries can be addressed separately.
I guess there are no more questions. We shall conclude the session. I'd like to thank all the participants who have attended for yesterday and today. For any of our for our future training programs on various other topics related to water and wastewater, we will keep mailing y'all and keep you updated about all our future programs. After the session, there would be a feedback form. Kindly fill it, and content that is a training content and the certificates would be provided to you by email. Do stay in touch. I would also like to inform that you could also view our magazine, which is right now digital. We are on magazine.watertoday.org, wherein we also provide our training program details. We also have 80 subscription offers that go on for the magazine, wherein you can also be a subscriber and attend our training programs as subscribers too. So thank you all once again, and thank you, Mr. Prakash, for your time. I
Have a
wish everybody a great weekend and good evening too.
yeah. Good evening, everyone. Have a good weekend. Have a wonderful 2021. Let it be a much more successful year for everyone than what last year. Okay? All the very best. Have a good evening.
Thank you.